This is 2019 AIME II problem number 15, and here is a view of this problem. We are given a acute triangle ABC and the circumcircle of our triangle. We can see the altitudes from the points B and C, and the feet of the altitudes are P and Q. I'll call the remaining feet as R. And we are also given some length segments. So when you extend PQ, you let it intersect the circumcircle at the points X and Y. And we are told that XP measures 10, PQ measures 25, and QY measures 15. So as a result, we want to calculate AB times AC, the lengths, the side lengths of our triangle. So this is a standard configuration. First of all, let me give some credits. The problem is due to DJ Mathman, and I would like to provide two solutions to this problem. The first solution is the official solution by Michael Tang, and the second solution is due to Trumpeter. Both solutions I'm following from the AOPS community page, and you can go and check the details from that as well. All right, so like I said, this is a standard configuration. Now that I know what the question is about, I can just augment the actual picture. Okay, there you go. So we can work on a bigger picture. So what I will do is I will first draw the orthic triangle. Already PQ is there, so all I need is to extend QR and PR. And at this stage, I will be doing a little bit angle chasing. Notice that quadrilateral ABRQ is cyclic. It's obvious by the fact that you have angle ARB and AQB are both 90-degree angles. And because this is cyclic, it turns out that this implies angle BAQ plus angle BRQ is 90 degrees. Sorry, I should say 180 degrees. And as such, the complementary angle, this angle here is also measures A. By the same token, you can easily see that this angle here will also measure A as well. And if you focus your attention on, say, quadrilateral BPQC, which is also cyclic, that would tell you that this angle here is also B, and as a result, this part would be B as well. And finally, focusing our attention on cyclic quadrilateral, let me see, oh yeah, BPQC again, it's clear that this is angle C, and APRC again, this angle is also C. So this angle is also C. So what that does is the orthic triangle, in a way, splits the region of triangle ABC into four pieces. So we have a triangle in the middle, which we called it as the orthic triangle. The angles of the orthic triangle, I think it's clear that if this angle is A, this one is 90 minus A, this one is 90 minus A. So as a result, our A is an angle bisector of our orthic triangle PQR. And so the whole angle here is 180 minus 2A. And the same thing will happen for the other two angles of our triangle. So therefore, angles of the orthic triangle PQR, orthic, we call it the orthic triangle, are 180 degrees minus 2A, 180 degrees minus 2B, and 180 degrees minus 2C. Like I said, this is a very well-known configuration. This orthic triangle and the medial triangle are very well studied configurations. So this angle, notice that is B, this angle is A, this angle is C. So basically what we have is we have four similar triangles. So triangle ABC is similar to triangle ABC, AQP. You can just chase the angles. Oops, sorry for that. AQP, which is also similar to triangle, say, RBP. Triangle RBP, and that's also similar to triangle RQC. Triangle RQC. Okay, so these are a good way to start solving the problem. For instance, you can start with the fact that triangle AQP is similar to triangle RBP. AQP, RBP, I think it's correct. Okay, so therefore this would imply that, for instance, AP to PQ, AP to PQ, AP to PQ is simply equal to RP to PB, RP to PB, and that would simply imply that RP is equal to AP times PB divided by PQ. And finally, you can use power of the point P to establish AP times PB is just equal to XP times PY. So therefore we can replace it. So that would further imply, okay, let's create some space here. So I need probably a bit more space now. So that would be equal to, again, pop power of point at the point P here. That's what we are using. So AP times PB is the same as XP times PY, XP times PY, all divided by PQ. And now, because XP is 10 and PY is 25 plus 15, 10 times 40 divided by PQ, PQ is 25. So we have the length RP, which is, I believe, 400 over 25, which is 16. Okay, so by the same token, you can easily also calculate RQ as well. Similarly, RQ, well, obviously you will be using triangle, for instance, APQ and RQC this time. But it's the same idea, and then you will be using power of the point Q. And so that you should get that RQ is simply equal to 21. So let's mark these also. So we have this one is 16 and this segment here is 21. Awesome. At this step there are multiple approaches that one can employ. One of the approaches is in line with the incenter-excenter lemma, and it is the fact that notice earlier that I mentioned that this is an angle bisector. So H, the orthocenter of our triangle ABC, happens to be the incenter of triangles RPQ. So H is the incenter, and it turns out that A is the R excenter. Okay, so why? Because R excenter of a triangle RPQ again. So the reason is, again, angle chasing. If you extend PR, because BPR, so this angle is also C, as you can see. Why? Because it's a vertical angle with this one. And so this is an angle bisector, external angle bisector of triangle RPQ. As a result, if you do the same business here, if you extend this angle is also B, again, another external angle bisector. So this is really the, let's call it R excenter of, so excenter meaning the center of the X circle opposite the vertex A of triangle PQR. And the question is to find the distance AB and multiply it with AC. So therefore B is obviously the Q excenter. So B happens to be the Q excenter of the same triangle of triangle PQR, and so on. And similarly, we would have C is the, so C is congruent to the P excenter of triangle PQR as well. So now the problem reduces to this. So you have a triangle with side lengths 16, 21, and 25, and we want to find the distance between the excenters basically. So for that, let's go ahead and draw a new picture. 16, 21, 25 are the side lengths. Okay, so there you go. Let me go ahead and first draw a circle. Okay, there you go. Okay, so we have this new triangle. Let's call it ABC now, but in reality it's the triangle RPQ. I'm just following the notation of DJ Mathman, so you can later on go to AOPS and check the details of the proof again. ABC. So we have this length is 16, that one is 21, and this one is 25. And we want to find the distance between the excenters of this triangle. So let's make sense one more time. 16, 21, 25. So I want to find, for instance, AB would be the excenter, the distance between those that are adjacent to 16 and 25. So 16 and 25. So basically I want the B and the A excenters, and I want to calculate that distance. So basically I can just extend this. We'll just identify where the angle bisectors meet. So probably they meet somewhere here. And so this is the point IB. And in a similar way, well, obviously it will be collinear, right? So with this guy, so there's a lot of, okay, so if you extend this one, the angle bisector seems to be somewhere around here. There you go. So you can label this point as IA. Like I said, IB, C, IA are collinear, simply because of some simple angle chasing. Let's go ahead and do that angle chasing if you guys want. So that would be fun. So we have somewhere here is the incenter of our triangle ABC, let's say I. Okay, there you go. Okay, let's chase a little bit of some angles so that we have full confidence of what's going on. So let's go ahead and use red color, for instance. So obviously I is the incenter, so this is C over 2. That angle here is C over 2. And because we have an X center here, so this one is 90 minus C over 2. This one is 90 minus C over 2. But again, this is an angle bisector as well. So the whole thing was 180. So again, this is 90 minus C over 2, 90 minus C over 2, and then boom. So you have some vertical angles here. And as a result, that suggests that IAC, IB are collinear, basically. So maybe I might want to, yeah, my picture a little bit, move that point to this side so it's more clear. So somewhere more like this. Okay, good. So let's make note of that. So IB, CIA, CIA collinear. That's pretty neat. Now the last idea is to measure the length IA, IB, right? So the way I will do it is IA, IB, I will split it into two pieces, IAC, because now we know that these points are collinear, plus CIB, CIB. And for that, we will create some right triangle. So if you drop a perpendicular here, then we can make some calculations. This angle here is 90 minus C over 2. As a result, this angle here is basically C. And we can calculate IAC to be what? You can call it, well, let's call this point as, well, it happens to be the midpoint of BC. I would, wait, is it? No, it's not. All right, so, okay, so let's do a couple of tricks here. So let's drop the perpendicular here as well. I'll call this point as D and this point as E. Forget about the 24.5 for the time being. And I need to calculate EC. Let me go ahead and remind you of a very well-known, another fact which is very well-known and you guys would remember it. So if you have the incircle of a triangle, let's say triangle ABC, I hope I'm not confusing people here. Do you guys remember that these distances are equal because of equal tangents? Those two distances are equal and this one is equal to that distance. And in fact, we can calculate these distances to be S minus A, S minus C here, S minus B, S minus B, S minus B, where S is the semi-perimeter. So where S is equal to 1/2 A plus B plus C. Now that's the first fact that I wanted to mention. And the second fact is the following. Actually, I might need more space here, so let's move this over here. S semi-perimeter. All right, the second fact is the following. if you label this point here as D, D is the touch point of the in circle. Obviously, it's perpendicular to the center I. So I is the incenter. Well, what you can do is, if you locate the excenter, let's say it like this quickly, so maybe somewhere around here. Suppose that this is IA, the excenter, meaning if you draw the circle here, the X circle, let's go ahead and do that. So I drop this tangent, this perpendicular here, so you have this nice circle which will be tangent to these sides, right? So over here and maybe over here too, and you have this nice circle. Okay, so my next claim is the following. I claim that BD, so BD here is equal to, if you call this point here, is equal to EC. So basically I claim that this distance here and this distance are just equivalent, and you can easily do that also using equal tangents. So if you call this point here as K and this one is L, AK is equal to AL, and then you can do some length chasing. Let me quickly do it, and then we can move on. And to be honest, I don't even need these S minus C, S minus B business. I will just get rid of all of them. All I need is the fact that they are congruent. So I'll just label them as X and X, Y and Y here. Well, I'll call this one as Z. The whole thing is Z, so therefore I'll call this one as T here, EC, I'll call it T. So therefore this one would be Z minus T. Okay, I hope people can see that. DE is Z minus T. My goal is to show that Y is equal to T. Alright, so but notice that BK is equal to BE as well because of equal tangents there. So as a result, Y plus Z minus T. So this one is Y plus Z minus T here. And similarly, EC is equal to CL. So this distance is also T. So finally, AK is equal to AL by equal tangents with respect to point A, with respect to that big circumcircle. So which is AK, I can split it as AB, so implying AB plus BK equals, and AL is just AC plus CL, AC plus CL. Now AB is just X plus Y, as you can see in the picture, and BK is just that monster there, Y plus Z minus T equals AC is just X plus Z, and CL is just T. Aha. And so as you can see in this picture now, we would have quite a few things cancel. So the x's here cancel, so this x will cancel with this x, the z's will cancel, so we will be left with 2y on the left hand side. I'll move that minus t to the other side, is equal to 2t, suggesting y is equal to t. So that's pretty good deal. Okay, back to our picture. So we have just proven that BE here is equal to CD. So CD is S minus C, BE is S minus C, so B is S minus C. I'll claim that CE obviously is equal to CD plus ED, CD plus DE. But we have established that CD is equal to BE. So it's just BE plus, and I will just swap the letters here, ED, so which is just BD. But BD is just, like I said earlier, so this whole distance here is just S minus B from this configuration. Remember earlier I mentioned it. So this is S minus B. So CE is S minus B, and we have this right triangle here. So in this right triangle, so now we are done, huh? So pretty much. So our goal was to establish IAC. Well, IAC is just CE, so CE times sine C. Wait, is that so? No, of course not. Because look, that's not what I expected. If this is 90 minus C over 2, after you drop a perpendicular here, this one is C over 2. Okay, sorry for that. Okay, so therefore, okay, one more time. IAC is just, because sine C over 2, here is EC over IAC. So therefore, it is EC times, and EC is just S minus B. S minus B all divided by sine of c over 2. Oh boy, that has been quite a few things. Okay, and by the same token, we can easily calculate IBC as well as s minus a over c minus over sine c over 2. That's okay. Now we can combine these two. So the denominator is the same. Okay, let's move it over here. So the denominators is the same. So you get 2c, sorry, 2s minus a minus b over sine of c over 2. But that's just a plus b plus c minus a minus b. So it's just c over sine c over 2. And by the same token, so this is IA, IB. We also needed to calculate wait a second, IA, IB. I did that one. I think we also needed to calculate IA, IC. Let me see. Yes, we also needed, so we need to calculate AC in the original picture, which is the one adjacent to 25 and 21. 25 is the long BC, 21 is here, so it is IA, IC, yes. We also need IAIC, but again, just by the same token, if IAIB is equal to this, analogously you can calculate this to be B over sine of B, angle B over 2. And we need the product of these two quantities now. Okay, so that's pretty convenient now. So the desired product, IAIB times IAIC is simply equal to B times C divided by sine B over 2 times sine of C over 2. And at this step, we need to calculate sine B over 2 and sine C over 2, but we can easily do it using a law of cosine type of argument. Going back to our original picture, we know the side lengths of our triangle are 16, 21, and 25. You can easily find cosine of B by the law of cosines. Let me write that down. Law of cosines on triangle ABC will give you 16 square equals 21 square plus 25 square minus 2 times 21, 25 times cosine of angle B. And from here, okay, I'll leave it to you to do the bash. Cosine B comes out as 27 over 35. And by the same token, if you apply law of cosine, this time focusing on this angle C here, you can also find cosine C to be, and please do the bash, 11 over 20. Now, we can use double angle formulas. Let's open some space here. For cosine, obviously cosine B is equal to, using double angle formulas, 1 minus 2 sine square of B over 2. But from here, sine B over 2 is simply equal to square root of 1 minus cosine of B over 2. But we just calculated cosine B, right? 1 minus 27 over 35 over all divided by 2. So if you do the algebra here, I think this comes out as square root 4 over 35. And you do exactly the same strategy to calculate sine of C over 2 as well. And this one comes out as a square root of 9 over 40. Now we can combine all of it together to plug in into this expression here. Let me put a sign here. So that whole expression as a result is equal to, so B times C is 21 times 16, all divided by the sines, which we calculated here, square root 4 over 35 times square root 9 over 40. And the algebra, finally, this thing comes out as 560 root 14. And the question was asking for the sum of these two numbers, which is 574. So that's just the first solution. But the second solution is much simpler, actually. Okay, so the previous official solution was somewhat annoying, and here's I believe a better solution from Trumpeter in AOPS user Trumpeter. And so the idea is the following. So again, we know XP is 10, PQ is 25, and QY is 15. We can go ahead and again draw the orthic triangles, the orthic triangle I should say. And so basically if you label this point as R, we just connect R and Q, and we do the same thing on the other side, P and Q. Instead of angle chasing this time, okay, so this is supposed to be a straight line. I don't know why it's making all these curves. All right, so let's go ahead and start with, I'll establish the fact that PQR is a 16, 21, 25 triangle one more time, this time directly using some trigonometric identities and also power of point. So pop at P, if you use power of the point P, that will give you 10 times 40, which is, okay, let's just write it, I guess. 10 times 40 is equal to AP times PB, AP times PB. Now we will go ahead and find AP times PB, yes. And we will go ahead and find a trigonometric expression for both of these quantities. So in the case of AP, if you will, I can make use of this angle over here and the fact that AC is equal to C. So therefore, I think it's clear that AP would just be equal to C times cosine of angle A. C times cosine of angle A. Again, all I did was to use, oh sorry, this is not C, this is a B, sorry. This is a B. AC is just B, yes. B times cosine. Where did I find this? All I did is focusing on right triangle APC. AC is B, and so therefore AP would be just B cosine A. And by the same token, PB can also be represented in terms of angle C this time. PB, we can do it in terms of angle B, I should say, yes. Angle B is here, so that would be, and this one is measurement A, so therefore this would be A cosine of A cosine B, A times cosine of B. And we'll do pretty much the same thing for the point Q, so using power of the point Q, so that would be 15 times 40, 15 times 40 equals AQ times QC, AQ times QC. Well, AQ is, again using angle A, that would be C cosine A, C times cosine of angle A times, and then QC, this time I can use angle C here, so that would be A cosine C, A times cosine of angle C. Okay, lastly, we need the following. Both of these expressions here have this term A cosine A, and I will establish the value of this. I claim that A cosine A is 25. And so basically it's equal to length PQ. So why would that be so? It follows directly from dilation and some reflection basically. So notice that these two angles are both B, obviously. It's clear, right? So because BPQC is cyclic, so this angle is B, that angle is B. And by the same token, this angle here is a C, and this angle here is a C. So our triangle ABC, let's write that down. Triangle ABC is similar to triangle AQP, but the order is different. So what we can do is we can first reflect this thing, across angle bisector, across A angle bisector, and then we can just shrink it. So we just reflect across A angle bisector. For instance, the way it will happen is if you extend AB here, so B reflected across the angle bisector, so B will fall, I don't know, maybe somewhere around here. So we will call this B prime, and then C will fall somewhere here, C prime, after the reflection. So now if you draw this line, because this angle here is a B and this angle here is a C, those two lines are parallel. PQ is parallel to C prime, B prime. And as a result, these two triangles are in dilation. APQ and AC prime B prime are in dilation. Now, what is the dilation ratio? I claim the dilation ratio is cosine of angle A, this angle, the cosine of this angle. Okay, so let's establish that. But first, I want to get rid of this B prime C prime business. It's totally redundant. All I wanted to is to show you guys that we can do it. Okay, so let's erase. Okay, good. One more. All right. So where does this dilation come from? There's a couple of ways you can convince yourself. One of the ways is the following. So BC measures A here. So BC is associated with PQ, right? So therefore, here this implies BC to PQ, BC to PQ is equal to, say, AC to AP, AC to AP, and finally it's equal to AB to AQ, AB to AQ. Let's go ahead and establish, for instance, one of these. So this way we would know the ratio of the similarity, right? So the ratio of the dilation centered at point A, if you will. All right, so AC over AP. AC is the whole thing, AP is the opposite side. What I can do is, I just noticed that on right triangle APC, AP is just AC, which is just B, B cosine of A, and I think we made use of it earlier, right? Or so, yeah, here. AP was B cosine A. Hey, AP is B cosine A, and AC is just B, so therefore the similarity ratio here is, actually let's write it over here. Come on. Okay, so my pencil just came out. Okay, so there you go. So let's rewrite it. AC is just a B, and AP we established is just B cosine A, B times cosine of angle A. These two cancel out, and exactly, so we have this ratio 1 over cosine A, if, well, in that case, because the dilation going from here to here, but the dilation going from here to here would be cosine A, basically. Wait a second, the other way around. But anyhow, so I think it's clear now. As a result, therefore connecting it now with combining it with this result, these two, so we have that BC over PQ equals 1 over cosine of angle A, and therefore suggesting that PQ itself is just BC cosine A, or if you will, A times cosine of angle A. That's nice, but PQ was just 25. That's pretty cool. So therefore this whole thing reduces to 25 times B cosine B, and this one is just 25 times C cosine C, C cosine of angle C. Okay, maybe a bit smaller. Yeah, so that's pretty neat. And obviously they are equal to 400 and 600 here. Oh, wait. 600 here. Wait, that shouldn't be 600. Okay, I messed up this one. So this one here is 35. Sorry, this is a 35. This one is at 35. There you go. So it's 525 actually. So this monster here is 400, and this one here is 525. So simplifying, we get B cosine of angle B is equal to 400 over 25, which is 16. And from here we get that C cosine of angle C is simply equal to 21. But by the same reasoning and dilations, PQ is just A cosine A, PR is analogously, so let's write that down, analogously, PR is just equal to AC, which is just B, B times cosine of angle B, and that's apparently equal to 16. And similarly, QR is equal to C times cosine of angle C, and that one is equal to 21. And there you go. So we were able to derive the lengths using a totally different idea, namely dilation. And now final step is to calculate the distance AB and AC separately and then multiply them out. So for that, what I will be doing is I will be using this property of the orthic triangle, namely the fact that the orthocenter happens to be the incenter of the orthic triangle PQR. We proved it in our first solution that these two angles are congruent, and they both measures 90 minus A. These two angles are congruent, they both measure 90 minus C, and these two angles are congruent, they both measure 90 minus B. So therefore the three angles of the orthic triangles are 180 degrees minus 2A, 180 degrees minus 2B, 180 degrees minus 2C. So I will go ahead and use double angle formulas now to get the desired result on these triangles. So basically what I have is the following. We will make a combination of double angle formula and law of cosine, basically. So let's begin. So for instance, let's consider the angle cosine. Let's see this angle over here. So this one is 180 minus 2A, as you know. So cosine 180 degrees minus 2A. If you want, we can do it first. We can calculate this one using law of cosine, and I think in my first solution I already calculated this one, right? So it is just 25 sorry, hold on. No, it is not 25 square. It is 16 square plus 21 square minus 25 square, all divided by 2 times 16 times 21. (11/20). Okay, got it. Now lastly, notice that we already know b cosine b is 16 and c cosine c is 21. Okay, so let's now use the double angle formula. I'll just use it for this one and this one. Remember, all we need is cosine b and cosine c here, and then we'll just plug it in basically. It would be very straightforward, I hope. We'll start with this one. So that's just cosine of 180 minus 2b. If you interpret it as a double angle, that would be cosine of 2 times 90 minus 2b. And that's just equal to 2 cosine square of 90 minus 2b minus 1. And well, the left hand side is apparently equal to 27/35, and on the right hand side we have 2 times cosine square of cosine 90 minus 2b is just sine 2b. So we have just, oh sorry, this one is supposed to be just a b, sorry for that, 90 minus b here. Okay, so there you go, cosine 90 minus b, which is just sine b. Okay, awesome. So 2 sine square of b minus 1, and that would just give us so moving the 1 to the other side, so 35 plus 27, and then we will eventually divide by 2 in the end. So that will give us sine square of b equals, I believe, 31/35, but again we needed the cosine b, not sine b, so therefore this would imply 1 minus cosine square of b is just equal to 31/35, and from here that would imply cosine square of b is equal to 4/35, or just taking the square root, cosine b is just square root of 4/35. In a similar way, let's make use of the same thing for the other one. So cosine of 180 minus 2c is just cosine of 2 times 90 minus c, and that's just 2 cosine square of 90 minus c minus 1, and that's just 2 sine square of c minus 1, but the left hand side, like we said earlier, is 11/20, so that would imply that sine square of c is just equal to 31/20, 31/40, and implying further that, well, sine square, so this is just 1 minus cosine square of c is equal to 31/40, which is 9/40, so square root 9/40. So finally this would imply cosine of c is equal to square root 9/40. So we have cosine B, cosine C. Time to plug them into this expression. So first this one, so B cosine B is 16, so therefore B is equal to 16 over cosine of B. B is equal to 16 over cosine of B, which is just this monster, square root 4 over 35. And similarly, C is equal to 21 over cosine of C. 21 over cosine of C is this, square root 9 over 40. And we need the product of these two. So B times C is equal to 16 times 21, all divided by square root 4 is just a 2, square root 9 is just a 3, and then in the denominator we have a square root of 35 times 40. So we can move it up. So these two cancel, we have an 8 here. These two cancel, we have a 7. So that would give us 56 times square root of, okay, so we can factor out 5 squared here. So there will be a 7 left here and an 8 left here. And the 8 we might as well just put it as a 2. So 7 times I think there's another 2 remaining. So 5 and 2 come out of the square root. So 560 square root 14 indeed it is. Oh, okay, so that's pretty much done. So basically what we did is just to use some trigonometric expressions to simplify to come up with the dimensions of this PQR orthic triangle, and then again just using further law of cosine and double angle formulas to wrap up the solution. I felt like the second solution is way easier than the first one. The first one, the student needs to be aware of these new constructions, namely the incenter-excenter lemma and some length bashing, which is the diameter of the incircle type of identities like we covered over here, the incenter-excenter lemma type of arguments here. So the first one is more configuration specific, if you will. Well, there's also some configurations in the second one as well, I would guess. But that's all for this question. Hope to see you guys in our next lecture.